Greetings, everybody. My name is David Alvarez Castillo, and I'm very pleased to participate in the Iguara 2020 video conference. The title of my talk is Accretion-Induced Collapse to Third Family Compact Stars as a Trigger for Eccentric Orbits of Millisecond Pulsars in Binaries. A few words about me. I work at the Joint Institute for Nuclear Research in Dubna, Russia, as well as in the Institute of Nuclear Physics of the Polish Academy of Sciences in Krakow, Poland, where I earned my PhD a few years back. I'm going to discuss the dynamical interaction of a binary with a circumbinary disk. This is motivated by the fact that there are some anomalous observations of orbital orbits of binaries with high eccentricities, in contrast to most of the binaries that follow a rather circular behavior, as you can see here in the figure on the left. A few points that are here represented by green stars and this magenta one have orbits with high eccentricity. It is explained, or it is conjectured, that these orbits can be produced by a creation of matter from a companion into a neutron star, which eventually creates a circumbinary disk from where the neutron star accretes matter further on. This work is the result of a collaboration that has been published in this journal, and it can be also available for free in the archive under this number. The equation of state that we consider represents or describes a hybrid neutron stars, and the approach we follow is the one of Hebler et al. That fulfills modern constraint on neutron stars, on the equation of state of neutron stars. So for this, if you look here on the right side figure, we see the densities that are meant to be found inside neutron stars, and a lower density we have some matter that is describes the crust of the neutron star. The typical equation of state is BPS, up to some point where we find the cross-core transition. And as you can see here, there's some degree of uncertainty in the equation of state that we choose to fulfill constraints. But as we go further into high densities, the degree of uncertainty grows, and over there we can parameterize or we can vary the parameters in order to describe different possibilities. So these high density parts are described by a polytrope that has got this function here, where the pressure is proportional to the baryon density to some gamma power. Each of these I corresponds to a different segment, and the equation of state that we have chosen is composed not only of 3 segments, but 4 segments, and we call it ACB5. So in order to build up this equation of state, we have to parameterize pressure as a function of baryon density. And from here, we can derive the other thermodynamical quantities like energy density, chemical potential, and so on. In particular, this equation of state features a strong first-order phase transition, which will end up creating an instability region in the mass radius diagram. And for this to happen, we can check that the Seidov criterion is fulfilled. That tells that the changing in the energy density at the phase transition should fulfill this equation, where P is the critical pressure at the transition and E is the energy density at the transition. The different regions are connected by imposing Gibbs conditions. That means that the pressures at the interface are the same, as well as the chemical potentials. So with this equation of state, we can study this scenario where a neutron star accretes matter and gets a spin up. So if you look here at this figure on the left, you can see the static configurations in black, following this black line. And as matter is accreted from the companion, the neutron star can spin up to a point, possibly up to a point where when it reaches the Keplerian frequency. That's the maximum frequency before matter starts to shed because of rotation. This dashed lines, blue dashed line, corresponds to matter that may be accreted, that can be gained by the star through accretion. In the case of this fraction is usually low. In the case of a very high accretion rate, the neutron star may end up in the so-called propeller regime, where because of rotation, no more matter is accreted. All the matter is rejected away because of the rotation. So once the neutron star reaches the maximum the maximum point of accretion, it might spin down and it might suffer a transition into a hybrid star. So for this scenario to happen, or to describe this scenario quantitatively, we have solved the following equations. So first, we start with we model rotation of uniform rotation of the neutron star by considering a rotating metric, and we apply some approximation on rotation by expanding the metric in terms of higher frequencies and neglecting them. This is the typical Hartree method. And once the neutron star is rotating, we can solve the equations for the gain of angular momentum with respect to the change on baryonic mass. What we have here is the specific angular momentum of the infalling particle and the innermost radius of the disk R0. We also have here the magnetic torque divided by the accretion rate. We have the co-rotating radius of the star. We have also the dipole moment of a star, mu. And with this equation, we can end up determining the dynamics. We have also entering in the equation the magnetic radius, and the magnetic field may change depending on the accretion rate. So basically, accretion can vary the magnetic field, and this is parameterized in this way, where Bi is the initial magnetic field and M is the accretion the mass accreted, divided by this parameter that regulates this accretion. The typical values, initial values that we need to solve these equations are the mass change, baryonic mass change, that is all about of 10 to the minus 9 solar masses, and initial magnetic fields of 10 to the 8 Gauss. So going back to the figure, so basically once the neutron star is in a point up to that has accreted mass and stop accreting, it might just spin down, and this spin down may increase the internal density, the density at the center of the star, triggering a transition into the hybrid configuration. And this possibility, there are two possibilities for this. This can be through a direct collapse. However, the direct collapse, because of some considerations, is meant to end up again in a circular orbit. But in contrast, the delayed collapse, the one that will happen not as fast as the direct collapse and will also follow the same trajectory as the direct collapse, may end up or may land in this region of stable configurations with actually eccentric orbits. If we look at the frequency of the newborn hybrid star, we see that there's a dependence on the gravitational mass of this newborn hybrid star, and we also see that some of the pulsars that have been measured in eccentric orbits have this behavior that is a linear behavior of the frequency with respect to the gravitational mass. So this model is actually very much a question of state dependent, which brings the possibility of studying dense matter inside neutron star by these scenarios, by this phenomenon. So for instance, here for this model ACP5, the transition occurs at 1.4 solar masses over here. And if we want to, for instance, have this line that describes the system going through precisely through this point, we need to change either the parameters of this multi-polytope approach, or we can use more sophisticated equation of state that include a better description of the quark matter in the interior, and we can find equations of state that will have the transition at 1.35. So, however, this is the behavior as the frequency rises as the baryonic mass grows. So this is our finding, and this is what I had to present today. Thank you very much.